Hello everyone! Let's expand our collection of tunnel effects with another shader. We've had several fascinating examples here, most of which looked very irregular and demonstrated a smooth flight through some kind of corridor. This time, we'll try something more irregular that could resemble flying into some unknown cave. So let's program it. Maybe the cave tunnel gave the impression that it uses some kind of pre-made texture, but in fact everything in this shader is generated using functions and calculations. So this time I'll also create a scene with an empty color rect, to which we apply the shader in the usual way. So let's right click the shader scenes folder, creating a new scene, a user interface, let's call it cave tunnel. OK, right-clicking the root node, add child node, color rect, and in the inspector I do the usual stuff, changing the color to black, expanding layout transition, and set the size to Full HD 1920 to 1080. OK, and scrolling down to the material section where I create a new shader material, click it and create a new shader mode, type shader mode canvas item, the name cavetunnel.gd shader, and let's put it to the shaders folder. Create, and it was automatically opened in the shader editor. Okay, and as usual, we can also delete everything we won't need in the code, leaving us with just a fragment function, deleting vertex and deleting the commented out light, Ctrl S to save. All right, so we can start coding. This is another example of a shader that uses a large number of uniform parameters. This time there will be 15 of them, so that we can adjust the color gradients, the structure of the tunnel walls, and other things. I will insert these parameters right at the beginning, and to make them easier to keep track of, I'll show you how we can organize parameters into groups. This is done using the group uniforms keyword, which I haven't used in any of our tutorials so far. So first I'll create a group called view because it will contain parameters related to displaying the resulting effect, resolution, zoom, speed, contrast, and so on. So let's do it here. Group uniforms, view. Okay, and now the mentioned parameters, uniform vec2, resolution equals vec2, and our full HD resolution 1920 and 1080. Okay, the second one is the zoom factor, uniform float zoom with a hint range, and the initial zoom I set to 1, and the range goes from 0.1 to, let's say, 4 with the 4 with the step point 0, 1. Okay, second parameter, third parameter is called speed. And as we know, it is meant to control the speed of the animation, another hint range, and the initial speed is 1 again. And it goes from 0 to 10, for instance, with a step point 0, 1. Okay, and the last parameter in this category, well, not last, but at this last for this moment, is contrast uniform float. Contrast with another hint range, and the initial contrast I set to 10, and it goes from the range from 1 to, let's say, 20, and again with a step point 0, 1. Okay, there will be two more parameters in the same group. The first is called fade, which we'll use to darken the central part of the tunnel if we want its far end to fade into darkness. So uniform float fade with a hint range, and initial fade I set to 0.25, and the range goes from 0 to 1 with a step point 0, 1. And I've named the second one bumpiness because we will use it to control the roughness of the simulated stone surface of the tunnel. Uniform float bum bumpiness hint range, and default bumpiness is set to 3, and it goes from 2 to 10, and 0.01 is the step. You may be wondering why I start the range from 2 and not from usual 1 or lesser. Well, actually, as we will see briefly, the lower values of these parameters caused very ugly visual artifacts, so this is why I set it to 2. Okay, and let's continue with the second group, which I'll call cave palette. So let's do it here. Group uniforms cave palette. Okay, and as the name suggests, we'll now add parameters that control the coloring of the individual parts of the cave. There will be 5 such parameters in total, and all of them are colored in RGB format, semicolon, so they will be of the type vector 3. Uniform vec3 color rock. I will explain the unusual names shortly, and with the hint source color and the initial color vec3, 0.02, 0.01, and 0.015. Okay, and let's save some time and copy and paste 4 times this line. 1, 2, 3, 4. And I will change the names, of course. This one will be color amber. The third one is color flame. The fourth one, color hot. And the last one, the fifth, is color core. Okay, and of course we will modify the default values as well. So the color amber is set to 0.35, 0.05, and 0.02. Color flame will be set to 0.9, 0.25, and 0.03. The color hot, its default value is 1.75 and 0.35. 30 I said, right? Yeah. And finally, the color core will be set to 1.97 and 0.85. Okay, so the color names correspond to the default settings, which evoke the impression of flying through a cave illuminated by fire. Of course, we can later change them to any other colors. And the last group of parameters will be called color mixing and will contain the transition values between the colors defined right here. So let's add the final group. Group uniforms, color mixing. Okay, and there are 5 colors, so there will be 4 transitions which look like this. A uniform float, edge amber with a hint range and the initial value 0.3, and it goes from 0 to 1 with the step point 0, 1, and I think I have the same range for all other parameters, so let's again save time and do some copies. 1, 2, 3, so we have 4 parameters, and I will rename the value the names to edge flame, edge hot, and edge core. Okay, and as I said, the ranges are the same and just the initial value. So for the edge flame, it is 0.6, The edge HOD has the default value set to 0.8, and finally the edge core is set to 1. Okay, so that takes care of all the parameters. We can take a look at the inspector, where instead of the usual shader parameters, we can see our 3 groups: view, cave palette, and cave mixing here, and their corresponding parameters. Let's expand view, cave palette, and color mixing, and we can see that it's necessary to reset the default values. Click, 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 and click, click, click here. Now it's correct and ready. Excellent. Let's continue with the code. We'll need 3 helper functions that we'll use to gradually build the final effect. First, I'll write a function for 2D rotation, which this time I'll use in a simplified and shorter form. So let's scroll down, and just before the fragment function, I will write this mat2 rotate with the parameter float a for angle, and now vec4, let's call it c, equals cosine of a minus vec4 0, 11, 33, 33, and 0, okay, and return mat2 of c dot xy and c dot zw. Okay, I should probably point out here that this function isn't an exact implementation of the typical rotation function you can see on the screen right now and that we commonly use in our tutorials. However, it's a sufficiently accurate approximation and perfectly adequate for our purposes, because this time we are using rotation only to increase the random factor and achieve a better looking final effect. As the second function, I'll write a simple color generator using the configured palette and color transitions. In other words, the parameters from the second and third groups. I'll use a combination of mix and smooth step functions, which will also contain several constants that I arrived at through various experiments. The result will look like this. Okay, let's put it right after the rotate function, vec3 palette, and with the parameter float t. Okay, as it's supposed to change over time. And now vec3 color equals the first mix of color rock, yeah, color amber, and smooth step with the parameters 0, edge amber, and t is the weight value. Okay, so this is the first mix, and finally at the end we will return the color. So let's write it here, return color, and now we need to add 4 more mixes with 4 more, three more mixes with 3 more edge values. So the second one, color equals mix of our color and with color flame, and again smooth step of edge amber, and this time minus 0.05 edge flame in the T. Okay, this is the first constant I mentioned, 0.05, and as I said, I came to them through experiments, and you can of course experiment with these values to change them as you will. All right, and 2 more lines, and I think I can copy and paste to save time. First, second, and now the third one is using color hot, and the last one color core. Okay, and we will have some other constants here. and of course the parameters as well. This one is color edge flame, and the last one would be edge hot. Okay, and edge flame minus 0.25 and edge hot plus 0.07, and this one goes from edge flame to edge hot, and the last one from edge hot to edge core. Okay, and this should be everything and hopefully correct. The last helper function is still to be written. It's more of a fundamental part of the entire shader, because this is where we'll define the shape of the tunnel and all the aspects that go along with it. It will be a somewhat more complex algorithm, but there is nothing in it that we haven't already done in previous tutorials. In short, it's a combination of ray marching and fractal Brownian motion, enhanced with various tricks and tweaks. I'll call this function ray march, and it will have a single parameter, the UV coordinates of the current pixel. So let's insert the function right after the function palette and before fragment float ray march, and as I said, with the parameter vec2 uv. Okay, so ray marching is, don't mind that, I will fix it eventually. Ray marching is quite an extensive topic that I've covered in an entire series of tutorials. So if you're interested in the details, I'll definitely recommend watching at least the first 2 episodes. You'll find a link to the full playlist in the video description. Here, I'll just briefly recap a few of the basics when we get to the corresponding lines of code. So let's start by defining 3 variables and returning the first one as the output of the function. So it will be float I equals 0, float dist equals 0, float sdf equals 1, and finally return I. Okay, so I will get to float is supposed to be here. Now it's correct. So I'll get to describing these variables in a moment, but first it would probably be a good idea to implement the fragment function so that we can monitor the intermediate results directly in the 2D editor. So I'll switch to the fragment function and write the usual beginning, moving the origin of the coordinates to the center, adjusting for the aspect ratio, and taking the zoom factor into account. Let's delete this comment and start. Vec2 uv equals uv minus 0.5, and then the aspect ratio uv.x is multiplied by resolution x divided by resolution dot y, and finally the zoom factor uv is multiplied by zoom. Okay, we continue by calling the raymarch function and using its result together with the contrast parameter, so it will look like this. Float v equals contrast divided by ray march with the parameter uv. Okay, so the variable v is it's called like that because it represents the brightness of the particular pixel, which is v in the definition of the HSV color model. We are performing a division to obtain the inverse value. The higher the number of iterations, the farther away is the resulting intersection, so we want to display it darker. Now we need to add darkened center of the tunnel with a smooth transition, which we can achieve using the smooth step function, of course, and the mix function. Again, the constants were chosen based on experimentation. So let's continue. Float dark center equals smooth step of 0.5. 75 and length uv. As we know, the length function is used to calculate circles, so this is exactly what we need for a cylindrical tunnel and its dark center of the same shape. And now the mix v is multiplied by mix of the fade parameter 1 and the dark center. Okay, I'll now make a small adjustment to the value of V so that it always stays slightly below 1 and the colors don't become overexposed. V equals minimum of V and let's say 0.95. Okay, and finally we'll output the color we get from the palette function. So color, the output variable in capital letters, is vector for the function palette with the parameter v and 1 for the alpha channel. Okay, so for now everything is monochromatic because the calculation in the Raymarch function hasn't been implemented yet. In fact, we are dividing by 0 here, which the Godot shading language interprets as NaN, not a number, so the result can look pretty much anything. So let's fix that and return to the Raymarch function, where we'll complete our algorithm. So, as I promised, let me say something about these variables. Raymarching is based on sending a ray from the camera through the current screen pixel. In each iteration, we extend this ray and determine whether it has intersected the surface of the object we want to display. The variable I, this one, is therefore the iteration counter, which we'll then use to determine the brightness of the resulting pixel. The dist variable, the second one, contains the current length of the ray, while SDF, this one, stands for signed distance field, a function that describes the surface of our object. And because we want to display a very bumpy tunnel, we'll gradually modify the SDF value in the following loop. So I'll write the definition of this loop. Let's continue. 4, and this is interesting. Just semicolon. I less than 99 in the SDF greater than 1e. Negative 4, which is I think 0.0001, and I plus plus and curly brackets. Okay, sorry, SDF, and not logical and, but 2 ampersands. Sorry, this is correct. Okay, so this is slightly different from the usual loop definition, where I normally use a construct such as float I from 0 at the beginning. This time I've left that part out because we define I at the beginning of the function so that we can return its value right here at the end. If we didn't do that, I would exist only inside the loop and wouldn't be accessible anywhere else. That's why the for definition starts with a semicolon. The second part, where we specify the loop termination condition, is also a little longer because we have 2 conditions here. We want to limit the number of iterations even if the ray doesn't intersect any object, while at the same time defining a small distance from the surface that we already consider an intersection. I described all of this in detail in the aforementioned Raymarching tutorial, so here we have it in a simplified form. And as we can see, the result has also changed. Let me just show all of that, although it's very dark, so probably not too visible. Anyway, and now we have something resembling a dark red color with a black circle in the center. So let's continue with the algorithm. As I mentioned, ray marching is based on extending the ray, so we'll do that as the first line in the loop right here. Dist is increased plus equals SDF times 0.3. Okay, so why do we multiply it by 0.3? It turns out that the recalculation of the SDF value is somewhat chaotic, or will be, it's not implemented yet, which would lead to greater inaccuracies than we'd like. By reducing this increment, we compensate for this chaotic factor. As the next line, we'll define a point in the 3D space for which we are performing this calculation. So the next line is vec3 p for point equals vec3 uv times dist, and the third component is dist simply. Okay, and because we want the tunnel to move, or rather the camera to move through it, we'll add the corresponding offset to the z coordinate. P dot z is increased by time times speed. Okay, we'll complete the basic algorithm with the formula for the inside of a cylinder, which forms the basis of our tunnel. So SDF equals 1 minus length of P dot xy. Okay, now we need to add something changed again. And now we need to apply fractal Brownian motion to create fractal structures on the tunnel walls. For this, we'll use another loop, this time with a slightly different nonlinear progression. So I'm continuing with a second loop, inner loop for float A from 2 A less than 600 and A plus equals A. Okay, and the curly brackets. I think that this part, A plus equals A, is probably the most unusual part of this loop definition. The reason is that we want to use a multiple of the point P at each iteration, but we don't want to increase these multiples linearly, as that would result in a pattern that is too irregular. So, in this way, the variable a doubles after each iteration. It starts at 2, then becomes 4, then 8, then 16, and so on. With the limit set to 600, this gives us 9 iterations. So we can define a vector q, which, as I mentioned, is a multiple of vector p. So inside this loop, let's do this. Vec3 q equals p times a. Okay. Now we'll apply the rotate function, which will be different in each iteration, once again increasing the level of chaos. Q dot xz is multiplied by rotate of A. Okay, all that's left is to add the final line, which will bring all this to life, as we'll see in a moment. So the core of the algorithm is SDF is decreased by minus equals absolute value of dot product of sine of Q, comma, and vec3 1. Okay, and this is divided by A times bumpiness. Okay, wait for it. Yeah, here we go, and the effect is complete. As we can see, we are subtracting the calculation from the SDF variable, which creates these chaotic distortions in the original smooth cylindrical structure. The absolute value and the sine are common building blocks in cases like this, and as is dividing by the bumpiness parameter, again multiplied by a different value in each iteration. What's interesting about this formula is the dot product, this one. which is a trick for writing the sum of three sine functions in a shorter form. It is sine qx plus sine qy plus sine qz. This gives us a composite curve, which we further layer in each iteration until we arrive at the result we can now admire on the screen. So let's try changing some of the parameters and observe the result. Yeah, everything is shown. So let's go to the inspector and, for example, let's work with the first group first, changing the zoom factor. Yeah. Speed, yeah, I think it's clear or stopped. Contrast, increased, decreased, and the fade area in the center. Now it's cancelled out. Now it's the maximum. And of course, bumpiness. Let's smooth out the sides of the cave a little bit, cave walls, or make it more. And we can see how it now shows the hints of the visual artifact. So that's why the least value here is 2. But of course, if you don't mind these white areas, just make it smaller. It's entirely up anyone. Okay, and we can of course change the colors and their transitions as well. Let's scroll down a little bit. Here we need to be careful because not every combination will produce a usable result. We need to be patient and change the values gradually. So for example, edge amber, and yeah, now we can see if I do it just over this edge and it becomes completely red. So that's why I say we need to be careful and do these experiments with great patience. And then we are rewarded with pretty nice and completely different results. If you want to, let's reset and change some colors. For example, if we want to fly through a poisonous or radioactive tunnel, we can do something like this. Yeah, it's definitely totally completely something else. And yeah, there are many ways to customize that. Let's reset everything to the default values. Thank you very much for watching. I think a tunnel like this could definitely enhance a lot of games, even if it's used just as a background for a menu screen or during transitions between individual levels. It could also be used to simulate, for example, something like flying through a wormhole, if we change the color palette to some kind of psychedelic combination. The important thing is that the calculation isn't particularly demanding, leaving us plenty of room for experimentation and further improvements. For now, take care, good luck with developing your games, and I'll see you in the next video.